Hello, 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 you guys. So, today we are going for part three of our backend journey. And last time we checked around like basic topics, how internet works. Not too much in detail, but very informative topics that every developer should know. Now, today we are actually, I forgot to check on this first, so the internet only. I directly went on how internet works, so we are going to do that. And yeah, let's go. Okay, so I think most of these are similar, only this one is different. So yeah. Sometimes I start a project like this one, like reading this roadmap, and I do it without thinking. I um I don't plan it. I don't research a lot. And this has been my general behavior. So like I have taken projects where I have no idea how I would implement it, which has has actually got me much better. Has got me like has made me very resilient, very strong, very smart. But there comes a point when you realize what you have done, and this time only, like it's happening right now, where I realize, okay, this is going to take like a year or something to complete, because this is like a lot. This is almost the entire computer science course, and I don't know how much time. Like if there are around 50 topics, then mostly it will take an year, and much more than that also. So I don't know, and that's probably if I can do it every day, probably less. But then I also have my job and other stuff that I have to attend to. You don't know, like the good thing about being this spontaneous is that it always becomes fun. It always stays fun, and uh, overthinking, in my opinion, does a lot of harm. Whenever I think or I plan something, I think, okay, I should do this, I should do that. I always come up with ways to say no at the end. It's not worth it. And whenever I go with the flow, okay, I just want to do it, and then I just start. And like the way I started this, it just came one day that I want to read this, and let's read it on the stream. And I started reading this, and at the end, I end up doing all those stuff. So the good thing about not thinking and doing stuff is that you actually complete it. The bad thing is that it becomes super hectic. So let's start with the internet. Computer networks. Okay, so this is a video. Let me see if the voice is. Yeah. Okay, so I think it's a video by Google Carrier Certificates, how computer communicates in a network. Cool. It seems like the same topics. But let's go. Let's try Google. Let's have a refresher.
Welcome to Course 2, the bits and bytes of computer networking. You might remember me from the lessons on the internet in the first course, but you also might have jumped ahead, in which case we're meeting for the first time. My name is Victor Escobedo, and I'm a corporate operations engineer. My passion for IT began way back when I was 9 years old, and my dad brought home our first computer. He was a mechanical engineer and started using the computer to help him with his CAD work. This was the first time I was exposed to computers, and later realized that you can install new software on it, including computer games. As I tinkered with the
Okay, so this is when I got exposed to computers. Like obviously, my school had computers, and like that was a blessing. But in fourth grade, I like my father told me. I was not a straight A student. I somehow just secured a A grade, not the A plus grade. So my father told and mother told me, my parents told me basically, that if you what do you want if you get the A plus score, and that's when I told I want a laptop. Um, they did not have the budget, but they did promise me, and I got A plus grade that year. Uh, so I did not get it for long after that, but obviously they could not buy it. But they had promised me. So in seventh grade, um, they finally were like, uh, we had a promise that we needed to keep, and now we are capable enough. So here's your laptop, and they bought me a good MacBook Pro. So they spent like a good amount compensating for everything. But yeah, that's how I got exposed to seventh grade. I would be around um so 5 plus 4 minus 9. So 12 years old. So when I was around 12, and that's when I started my YouTube channel. Uh, I wanted to show off like my new laptop and the things I can do with it. I also did a lot of things because I got that laptop. I actually invested in crypto. Like at that time, in eighth grade, I regretted so much. I had some Bitcoin in a wallet somewhere, which is lost, and I don't know. Like I would be so rich if I could find that, but obviously it's not traceable. So the saddest thing. But what can you do? Happens. Yeah, that's my laptop story.
Computer. Surely to my dad's dismay, I became more and more interested in how it worked and eventually started to open up the case and peek inside. I found pieces that could be removed and even some that shouldn't, learning through trial and error along the way. I couldn't really explain what it was, but
Yeah, I also opened my MacBook, and like it got like we had a computer. We had a computer since I was a child. It was a computer and a TV in one. So we had that thing, and we used it as a TV mostly. Uh, but yeah, I actually forgot about that. But yeah, so sometimes when it got was not working, like it was not a good device. When it did not work, my father actually like opened it and went through it and tried to get it to work, and but so that's when one time my MacBook got uh, like was not working, and that's when I opened it. I did not tell it to anyone, and a little dusting actually fixes it. So kudos to me.
I just found the mechanics of how it all worked together so fascinating. Looking back, these were the seeds that inspired my career. But you see, where I grew up, going to college and pursuing a career wasn't exactly talked about or heavily encouraged. I'm a first generation Mexican American, and there weren't a lot of people I knew pursuing a career in tech. My friends and family were mostly worrying about graduating high school and making sure they had jobs, not really thinking about longer term careers. My school didn't have the resources to offer many technical classes, and even though my father was working in mechanical engineering, computers were a tool to him, like a mill, ruler, or hammer. My parents encouraged me to work hard and pursue computers, but they couldn't really give me advice about college or a career in tech. To no real fault of their own, they just didn't have the experience necessary. When I decided to go to college, I decided to try my hand at computer science, since it could feed my curiosity for how computers work at a more fundamental level. I realized that having this foundational knowledge really allowed me to understand something for 12 years now, with the last 7 years being here at Google. I now work on managing deployments of large internal IT projects and various support teams. In my role as a corporate operations engineer, I'm responsible for understanding the impact system, but how they interact with all other systems in the how humans do. Take verbal communication as an example. Two people need to speak the same language and be able to hear each other to communicate effectively. If there are loud noises, one person might have to ask the other person to repeat themselves. If one person only somewhat understands an idea being explained to them, that person might ask for clarification. One person might address only one other person, or they may be speaking to a group, and there's usually a greeting and a way to close the conversation. The point is that humans follow a series of rules when they communicate, and computers have to do the same. This defines set of standards that computers must each other. Networking involves ensuring that computers can hear each other, that they speak protocols other computers can understand, and that they repeat messages not fully delivered, just like how humans communicate. There are lots of models used to describe the different layers at play with computer networking, but for this course, we've selected the TCP/IP 5-layer model. We'll
I'm getting a call back. Hello, this is working.
SI model, which has 7 layers. If you don't
Okay, so this is also working. Now, and I'll be right back. I need to do some work. I'm coming. Hmm. Hmm. Hello. Oh, I'm back with my zero years. Cool.
Just like how humans communicate. There are lots of models used to describe the different layers at play with computer networking, but for this course, we've selected the TCP/IP 5-layer model. We'll also be touching on the other primary network model, the OSI model, which has 7 layers. If you don't know what these models are or how they work, don't worry. We'll be deep diving into these
So I explained these models last time. So
topics throughout this course. It's super important to know these types of layered models to learn about computer networking because it's a really layered affair. The protocols at each layer carry the ones above them in order to get data from one place to the next. Think of the protocol used to get data from one end of a networking cable to the other. It's totally different from the protocol used to get data.
I thought I should turn off my fan. Yeah, it was providing background noise. And turn on my AC.
Data from one side of the planet to the other. But both of these protocols are required to work at the same time in order for things like the internet and business networks to work the way they do. Sometimes there are problems when computers on the internet or on these business networks try to communicate with each other, and often it's up to an IT support specialist to fix these problems. This is why understanding computer networking is so important. By the end of this course, you'll be able to explain all 5 layers of our model. Not only that, you'll be able to describe how computers determine where to send their messages and how network services like DNS and DHCP work. You'll also be able to use powerful tools to help you troubleshoot network issues. Are you ready? Let's dive in. To really understand networking, we need to understand all of the components involved. We're talking about everything from the cables that connect devices to each other to the protocols that these devices use to communicate. There are a bunch of models that help explain how network devices communicate, but in this course, we'll focus on a 5-layer model. By the end of this lesson, you'll be able to identify and describe each layer and what purpose it serves. Let's start at the bottom of our stack, where we have what's known as the physical layer. The physical layer is a lot like what it sounds. It represents the physical devices that interconnect computers. This includes the specifications for the networking cables and the connectors that join devices together, along with specifications describing how signals are sent over these connections. The second layer in our model is known as the data link layer. Some sources will call this layer the network interface or the network access layer. At this layer, we introduce our first protocols. While the physical layer is all about cabling, connectors, and sending signals, the data link layer is responsible for defining a common way of interpreting these signals so network devices can communicate. Lots of protocols exist at the data link layer, but the most common is known as Ethernet, although wireless technologies are becoming more and more popular. Beyond specifying physical layer attributes, the Ethernet standards also define a protocol responsible for getting data to nodes on the same network or link. The third layer, the network layer, is also sometimes called the internet layer. It's this layer that allows different networks to communicate with each other through devices known as routers. A collection of networks connected together through routers is an internetwork, the most famous of these being the internet. Hopefully you've heard of it. While the data link layer is responsible for getting data across a single link, the network layer is responsible for getting data delivered across a collection of networks. Think of when a device on your home network connects with a server on the internet. It's the network layer that helps get the data between these two locations. The most common protocol used at this layer is known as IP, or Internet Protocol. IP is the heart of the internet and most small networks around the world. Network software is usually divided into client and server categories, with the client application initiating a request for data and the server software answering the request across the network. A single node may be running multiple client or server applications. So you might run an email program and a web browser, both client applications, on your PC at the same time. And your email and web server might both run on the same server. Even so, emails end up in your email application and web pages end up in your web browser. That's because our next layer, the transport layer. While the network layer delivers data between two individual nodes, the transport layer sorts out which client and server programs are supposed to get that data. When you heard about our network layer protocol, IP, you may have thought of TCP/IP, which is a pretty common phrase. That's because the protocol most commonly used in the fourth layer, the transport layer, is known as TCP, or Transmission Control Protocol, while often said together as the phrase TCP/IP to fully
1 minute.
understand and troubleshoot networking issues, it's important to know that they're entirely different protocols serving different purposes. Other transport protocols also use IP to get around, including a protocol known as UDP, or User Datagram Protocol. The big difference between the two is that TCP provides mechanisms to ensure that data is reliably delivered, while UDP does not. Spoiler alert, we'll cover differences between the TCP and UDP transport protocols in more detail later. For now, it's important to know that the network layer, in our case IP, is responsible for getting data from one node to another. Also,
I'm not putting that much effort in knowing this because I already know all these topics. It's just more like a revision for me. If some of you are don't get like don't think don't copy me on this because if you are looking at it then for the first time you need to know all these well enough.
remember that the transport layer, mostly TCP and UDP, is responsible for ensuring that data gets to the right applications running on those nodes. Last but not least, the fifth layer is known as the application layer. There are lots of different protocols at this layer, and as you might have guessed from the name, they're application specific. Protocols used to allow you to browse the web or send and receive email are some common ones. The protocols at play in the application layer will be most familiar to you, since they're ones you probably interacted with directly before, even if you didn't realize it. You can think of layers like different aspects of a package being delivered. The physical layer is the delivery truck and the roads. The data link layer is how the delivery trucks get from one intersection to the next over and over. The network layer identifies which roads need to be taken to get from address A to address B. The transport layer ensures that the delivery driver knows how to knock on your door to tell you your package has arrived. And the application layer is the contents of the package itself. Lots of different cables and network devices can be used to allow computers to properly communicate with each other. By the end of this lesson, you'll be able to identify and describe various networking cables and networking devices. Computer networking is a huge part of the day-to-day role of many IT specialists, and knowing how to differentiate different network devices will be essential to your success. Let's start with the most basic component of a wired network, cables. Cables are what connect different devices to each other, allowing data to be transmitted over them. Most network cables have wires inside plastic insulator. You may already know that computers communicate in binary. The system at the receiving end is able to interpret these voltage changes as binary IE and Cat6 tables. These are keyers by changing the voltage between two ranges. The system at the receiving end is able to interpret these voltage changes as binary ones and zeros, which can then be translated into different forms of data. The most common forms of copper twisted pair cables used in physical characteristics, like Cat6 cables. From the outside, they all look about the same, and even internally, they're very similar to the naked eye. The important thing to know is that differences in how the twisted pairs are arranged inside these cables can drastically alter how quickly data can be sent across them and how resistant these signals are to outside interference. Cat5e cables have mostly replaced those older Cat5 cables because their internals reduce crosstalk. Crosstalk is when an electrical pulse on one wire is accidentally detected on another wire, so the receiving end isn't able to understand the data, causing a network error. Higher level protocols have methods for detecting less likely that data needs to be retransmitted. That means on average you can expect more data to be transferred in the same amount of time. You can transfer data faster and more reliably than Cat5e cables can, but because of their internal arrangement, they have a shorter maximum distance when used at higher speeds. The second primary form of networking cable is known as fiber, short for fiber optic cable, support beams of light. Unlike copper, which uses electrical voltages, fiber cables use pulses of light to represent the ones and zeros of the underlying data. Fiber is even sometimes used specifically in environments where there's a lot of electromagnetic interference, much more expensive and fragile. Fiber can also transport data over much longer distances than copper can without suffering potential data load in an office or at home. We're going to do a rundown of network devices in this video and the next one. Almost every IT specialist will have to interact with these sorts of devices on a regular basis. Cables allow you to form point-to-point networking connections. These are networks where only a single device at each end of the link exists. Not to knock point-to-point networking connections, but they're not super useful in a world with billions of computers. Luckily, there are network devices that allow for many computers to communicate with each other. The most simple of these devices is a hub. A hub is a physical layer device that allows for connections from a hub to determine if the incoming data was meant for them connected to a hub. One of these devices is a hub. A hub is a physical layer device that allows for connections from many computers at once. All the devices connected to a hub will end up talking to all other devices at the same time. It's up to each system connected to the hub to determine if the incoming data was meant for them or to ignore it if it isn't. This causes a lot of noise on the network and creates what's called a collision domain. A collision domain is a network segment where only one device can communicate at a time. If multiple systems try sending data at the same time, the electrical pulses sent across the cable can interfere with each other. This causes these systems to have to wait for a quiet period before they try sending their data again. It really slows down networking pulses. Collision all the most connections, but they're not super useful in a world with billions of computers. Luckily, there are network devices that allow for many computers to communicate with each other. The most simple of these devices is a hub. A hub is a physical layer device that allows for connections from many computers at once. All the devices connected to a hub will end up talking to all other devices at the same time. It's up to each system connected to the hub to determine if the incoming data was meant for them or to ignore it if it isn't. This causes a lot of noise on the network and creates what's called a collision domain. A collision domain is a network segment where only one device can communicate at a time. If multiple systems try sending data at the same time, the electrical pulses sent across the cable can interfere with each other. This causes these systems to have to wait for a quiet period before they try sending their data again. It really slows down network communications and is the primary reason hubs are fairly rare. They're mostly a historical artifact today. A much more common way of connecting many computers is with a more sophisticated device known as a network switch, originally known as a switching hub. A switch is very similar to a hub since you can connect many devices to it so they can communicate. The difference is that while a hub is a layer 1 or physical layer device, a switch is a layer 2 or data link device. This means that a switch can actually inspect the contents of the Ethernet protocol data being sent around the network, determine which system the data is intended. If you guess that this will lead to fewer retransmissions and a higher overall throughput, you're right. Hubs and switches are the primary devices used to connect computers on a single network, usually referred to as a LAN or local area network. But we often want to send or receive data to computers on other networks. This is where routers come into play. A router is a device that knows how to forward data between independent networks. While a hub is a layer 1 device and a switch is a layer 2 device, a router operates at layer 3, a network layer. Just like a switch can inspect Ethernet data to determine where to send things, a router can inspect IP data to determine where to send things. Routers store internal tables containing information about how to route traffic between lots of different networks all over the world. The most common type of router you'll see is one for a home network or a small office. These devices generally don't have very detailed routing tables. The purpose of these routers is mainly just to take traffic originating from inside the home or office LAN and to forward it along to the ISP or internet service provider. Once traffic is at the ISP, a way more sophisticated type of router takes over. These core routers form the backbone of the internet and are directly responsible for how we send and deal with much more complexity in making decisions about where to send traffic. A core router usually has many different connections to many other routers for traffic. When you open a web browser via a protocol known as BGP or Border Gateway Protocol that lets them learn about the most optimal paths to forward traffic. When you open a web browser and load a web page, the traffic between computers and the web servers could have traveled over dozens of different routers. The internet is incredibly large and complicated, and routers are global guides for getting traffic to the right places. All of the network devices you've just learned about exist so that computers can communicate with each other, whether they're in the same room or thousands of miles apart. We've been calling these devices nodes, and we'll keep doing that, but it's also important to understand the concepts of servers and clients. The simplest way to think of a server is as something that provides data to something requesting that data. The thing receiving the data is referred to as a client. While we often talk about nodes being servers or clients, the reason our definition uses a word as vague as something is because it's not just nodes that can be servers or clients. Individual computer programs running on the same node can be servers and clients to each other too. It's also important to call out that most devices aren't purely a server or a client. Almost all nodes are both at some point in time. Quite the multitasking overachievers. That all being said, in most network topographies, each node is primarily either a server or a client. Sometimes we refer to an email server as an email server, even though it's itself a client of a DNS server. Why? Because its primary reason for existing is to serve data to clients. Likewise, if a desktop machine occasionally acts as a server in the sense that it provides data to another computer, its primary reason for existing is to fetch data from servers so that the user at the computer can do their work. To sum up, a server is anything that can provide data to a client, but we also use the words to refer to the primary purpose of various nodes on our network. Got it? Cool. In some ways, the physical layer of our network stack model is the most complex of all. Its main focus is on moving ones and zeros from one end of a link to the next. But very complicated mathematics, physics, and electrical engineering principles are at play to transmit huge volumes of data across tiny wires at incredible speeds. Luckily for us, most of that falls within a different realm. What you, an aspiring IT support specialist, needs to know about the physical layer is much more approachable. By the end of this lesson, you should have a solid foundation in aspects of the physical layer that will allow you to properly troubleshoot networking. A bit is the new networks. Let's dive in. The physical layer consists of devices and means of transmitting bits across computer networks. A bit is the smallest representation of data and packets of data that we'll learn about when we cover the other layers. The takeaway is that it doesn't matter whether you're streaming your favorite song, emailing your boss, or using an ATM. What you're really doing is sending ones and zeros across the physical layer of the many different networks between you and the server you're interacting with. A standard copper network cable, once connected to devices on both ends, will carry a constant electrical charge. Ones and zeros are sent across those network cables through a process called modulation. Modulation is a way of varying the voltage of this charge moving across the cable. When used for computer networks, this kind of modulation is more specifically known as line coding. It allows devices on either end of a link to understand that an electrical charge in a certain state is a 0, and another state is a 1. Through this seemingly simple technique, modern networks are capable of moving 10 billion ones and zeros across a single network cable every second. Pairs of copper wires that are twisted together. These pairs act as a single conduit for information, and their twisted nature helps protect against electromagnetic interference and crosstalk from neighboring pairs. A standard Cat6 cable has 8 wires consisting of 4 twisted pairs inside a single jacket. Exactly how many pairs are actually in use depends on the transmission technology being used. But in all modern forms of networking, it's important to know that these cables allow for duplex communication. Duplex communication is the concept that information can flow in both directions, only goes in one direction, making it a simplex as possible, is by reserving 1 or 2 pairs for communicating in one direction. They then use the other 1 or 2 pairs for communicating in the other direction. So devices on either side of a networking link can both communicate with each other at the exact same time. This is known as full duplex. If there's something wrong with the connection, you might see a network link degrade and report itself as operating as half duplex. Half duplex means that while communication is possible in each direction, only one device can be communicating at a time. The final steps of how the physical layer works take place at the endpoints of our network links. Twisted pair network cables are terminated with a plug that takes the individual internal wires and exposes them. The most common plug is known as an RJ45, or registered jack 45. It's one of many cable plug specifications, but by far the most common in computer networking. A network cable with an RJ45 plug can connect to an RJ45 network port. Network ports are generally directly attached to the devices that make up a computer network. Switches would have many network ports because their purpose is to connect many devices, but servers and desktops usually only have 1 or 2. Your laptop, tablet, or phone probably don't have any, but we'll get to wireless networking in a later module. Most network ports have 2 small LEDs. One is the link light, and the other is the activity light. The link light will be lit when a cable is properly connected to 2 devices that are both powered on. The activity light will flash when data is actively transmitted across the cable. A long time ago, the flashing of the activity light corresponded directly to the ones and zeros being sent. Today, computer networks are so fast that the activity light doesn't really communicate much other than if there's any traffic or not. On switches, sometimes the same LED is used for both link and activity status. It might even indicate other things like link speed. You'll have to read up on a particular piece of hardware you're working with, but there will almost always be some troubleshooter underneath your desk. These ports are generally connected to the network via cables ran through the walls that eventually end at a patch cable. Additional cables are then generally ran from a patch panel to switches or routers to provide network access to the computers at the other end of those links. Wireless and cellular internet access are quickly becoming some of the most common ways to connect computing devices to networks, and it's probably how you're connected right now. So you might be surprised to hear that traditional cable networks are still the most common option you find in the workplace and definitely in the data center. The protocol most widely used to send data across individual links is known as Ethernet. Ethernet and the data link layer provide a means for software at higher levels of the stack to send and receive data. One of the primary purposes of this layer is to essentially abstract away the need for any other layers to care about the physical layer and what hardware is in use. By dumping this responsibility on the data link layer, the internet, transport, and application layers can all operate the same no matter how the device they're running on is connected. So, for example, your web browser doesn't need to know if it's running on a device connected via a twisted pair or a wireless connection. It just needs the underlying layers to send and receive data for it. By the end of this lesson, you'll be able to explain what MAC addresses are and how they're used to identify computers. You'll also know how to describe the various components that make up an Ethernet frame, and you'll be able to differentiate between unicast, multicast, and broadcast addresses. Lastly, you'll be able to explain how cyclical redundancy checks help ensure the integrity of data sent via Ethernet. Understanding these concepts will help you troubleshoot a variety of problems as an IT support specialist. Warning, a history lesson on old school technology is headed your way. Here goes. Ethernet is a fairly old technology. It first came into being in 1980 and saw its first fully published standardization in 1983.
I'm feeling very lightheaded and sleepy. But yes, we'll complete this. It's like 13 minutes divided by 2. 6.5.
Since then, a few changes have been introduced, primarily in order to support ever-increasing bandwidth needs. For the most part, though, the Ethernet in use today is comparable to the Ethernet standard as first published all those years ago. In 1983, computer networking was totally different than it is today. One of the notable differences in LAN topology was that the switch, or switchable hub, hadn't been invented yet. This meant that frequently, many or all devices on a network shared a single collision domain. You might remember from our discussion about hubs and switches that a collision domain is a network segment where only one device can speak at a time. This is because all data in a collision domain is sent to all the nodes connected to it. If 2 computers were to send data across the wire at the same time, this would result in literal collisions of the electrical current representing our ones and zeros, leaving the end result unintelligible. Ethernet as a protocol solved this problem by using a technique known as carrier sense multiple access with collision detection. Doesn't exactly roll off the tongue. We generally abbreviate this to CSMA-CD. CSMA-CD is used to determine when the communications channels are clear and when a device is free to transmit data. The way CSMA-CD works is actually pretty simple. If there's no data currently being transmitted on the network segment, a node will feel free to send data. If it turns out that 2 or more computers end up trying to send data at the same time, the computers detect this collision and stop sending data. Each device involved with the collision then waits a random interval of time before trying to send data again. This random interval helps to prevent all the computers involved in the collision from colliding again the next time they try to transmit anything. When a network segment is a collision domain, it means that all devices on that segment receive all communication across the entire segment. This means we need a way to identify which node the transmission was actually meant for. This is where something known as a media access control address, or MAC address, comes into play. A MAC address is a globally unique identifier attached to an individual network interface. It's a 48-bit number normally represented by 6 groupings of 2 hexadecimal numbers. Just like how binary is a way to represent numbers with only 2 digits, hexadecimal is a way to represent numbers using 16 digits. Since we don't have numerals to represent any individual digit larger than 9, hexadecimal numbers employ the letters A, B, C, D, and a MAC address is an octet. An octet in computer networking is any number that can be represented by 8 bits. In this case, 2 hexadecimal digits can represent the same numbers that 8 bits can. Now, you may have noticed that we mentioned that MAC addresses are globally unique, which might have left you wondering how that could possibly be. The short answer is that a 48-bit number is much larger than you might expect. The total number of possible MAC addresses that could exist is 2 to the power of 48, or 281,474,976,710,656 unique possibilities. That's a whole lot of possibilities. A MAC address is split into 2 sections. The first 3 octets of a MAC address are known as the Organizationally Unique Identifier, or OUI. These are assigned to individual hardware manufacturers by the IEEE, or the Institute of Electrical and Electronics Engineers. This is a useful bit of information to keep in your back pocket because it means that you can always identify the manufacturer of a network interface purely by its MAC address. The last 3 octets of a MAC address can be assigned in any way that the manufacturer would like, with the condition that they only assign each possible address once to keep all MAC addresses globally unique. Ethernet uses MAC addresses to ensure that the data it sends has both an address for the machine that sent the transmission as well as the one that the transmission was intended for. In this way, even on a network segment acting as a single collision domain, each node on that network knows when traffic is intended for it. So far, we've discussed ways for one device to transmit data to one other device. This is what's known as unicast in the destination MAC address. If the least significant bit in the first octet of a destination address is set to 0, it means that Ethernet frame is intended for only the destination address. This means it would be sent to all devices on the collision domain, but only actually received and processed by the intended destination. If the least significant bit in the first octet of a destination address is set to 1, it means you're dealing with a multicast frame. A multicast frame is similarly set to all devices on the local network segment. What's different is that it will be accepted or discarded by each device depending on criteria aside from their own hardware MAC address. Network interfaces can be configured to accept lists of configured multicast addresses for these sorts of communications. The third type of Ethernet transmission is known as broadcast. An Ethernet broadcast is sent to every single device on a LAN. This is accomplished by using a special destination known as a broadcast address. The Ethernet broadcast address is all Fs. Ethernet broadcasts are used so that devices can learn more about each other. Don't worry, you'll be learning more about broadcast and a technology known as address resolution protocol later in this course. But for now, let's move on to dissecting the Ethernet frame. To wrap up, we'll round out your understanding of the basics of networking by dissecting an Ethernet frame. Understanding the networking basics is the first step in building a really strong data being sent across a network link. The term data packet isn't tied to any specific layer or technology. It just represents a concept, one set of data being sent from point A to point B. Data packets at the Ethernet level are known as Ethernet frames. An Ethernet frame is a highly structured collection of information presented in a specific order. This way, network interfaces at the physical layer can convert a stream of bits traveling across a link into meaningful data, or vice versa. Almost all sections of an Ethernet frame are mandatory, and most of them have a fixed size. The first part of an Ethernet frame is known as the preamble. A preamble is 8 bytes, or 64 bits long, and can itself be split into 2 sections. The first 7 bytes are a series of alternating ones and zeros. These act partially as a buffer between frames and can also be used as the SFD, or start frame delimiter. This signals to a receiving device that the preamble is over and that the actual frame contents will now follow. Immediately following the start frame delimiter comes the destination MAC address. This is the hardware address of the intended recipient, which is then followed by the source MAC address, or where the frame originated from. Don't forget that each MAC address is 48 bits, or 6 bytes long. The next part of an Ethernet frame is called the ether type field. It's 16 bits long and used to describe the protocol of the contents of the frame. We'll be doing a deep dive on what these protocols are a little later. It's worth calling out that instead of the ether type field, you could also find what's known as a VLAN header. It indicates that the frame itself is a technique that lets you have multiple logical LANs operating on the same physical equipment. Any frame with a VLAN tag will only be delivered out of a switch interface configured to relay that specific tag. This way, you can have a single physical network that operates like it's multiple LANs. VLANs are usually used to segregate different forms of traffic. So you might see a company's IP phones operating on one VLAN, while all desktops operate on another. After this, you'll find the data payload of an Ethernet frame. A payload, in networking terms, is the actual data being transported, which is everything that isn't a header. The data payload of a traditional Ethernet frame can be anywhere from 46 to 1500 bytes long. We have what's known as a frame check sequence. This is a 4-byte or 32-bit number that represents a checksum value for the entire frame. This checksum value is calculated by performing what's known as a cyclical redundancy check against the frame. A cyclical redundancy check, or CRC, is an important concept for data integrity and is used all over computing, not just network transmissions. A CRC is basically a mathematical transformation that uses polynomial division to create a number that represents a larger set of data. Anytime you perform a CRC against a set of data, you should end up with the same checksum number. The reason it's included in an Ethernet frame is so that the receiving network interface can infer if it received uncorrupted data. When a device gets ready to send an Ethernet frame, it collects all the information we just covered, like the destination and originating MAC addresses, the data payload, and so on. Then it performs a CRC against that data and attaches the resulting checksum number as the frame check sequence at the end of the frame. This data is then sent across a link and received at the other end. Here, all the various fields of the Ethernet frame are collected, and now the receiving side performs a CRC against that data. If the checksum computed by the receiving end doesn't match the checksum in the frame check sequence field, the data is thrown out. This is because some amount of data must have been lost or corrupted during transmission. It's then up to a protocol at a higher layer to decide if that data should be retransmitted. Ethernet itself only reports on data integrity. It doesn't perform data recovery. You've gotten the basics of networking down. Nice work. Next up is a quiz. You got this. But even if you don't, just review the material until you get more comfortable with this stuff.
Congratulations on finishing this lesson from the Google IT support.
Nice. We have learned these topics like in our readings, and I am too tired today, so we'll finish this.